everyone, today we are going to learn the standard curve method. It is usually applied when there's only one component absorbing at measuring wavelength in analytical solution. So, what is a standard curve? The standard curve is also called the calibration curve or the working curve. First, prepare a series of standard solution with different concentrations under certain condition, and then determine the absorbance of each standard solution in the series at a fixed wavelength and the light path. Make the curve of absorbance A and concentration C, which are straight lines through the origin, namely the standard curve. We take the determination of ferrous content in the sample as an example. Due to the low concentration of ferrous, it needs to have a Calor reaction before the spectrophotometric measurement. Ferrous and phenazrolene have the Calor reaction at pH 2 to 9 to produce a stable orange-red complex with maximum absorption wavelength at 510 nanometer. Different volume of ferrous standard solution is transferred in a series of volumetric flasks with the same volume, and mixed with suitable amount of chromogenic reagents and other reagents to have the Calor reaction completely under the best conditions. The product solution is then diluted to a constant volume. The corresponding reference solution is also prepared following the same process. The absorbance of each solution is subsequently measured under the optimum conditions, based on which the standard curve of absorbance A and concentration C can be made. Follow the same procedure, the absorbance AX of test solution is measured after the Calor reaction. The concentration of the test solution CX can be calculated by AX from the standard curve. In the analysis of visible spectrophotometry, it is generally necessary to select an appropriate reagent to react with test component in the sample and produce the Calor compound, the absorbance of which can be determined. Then, what exactly is this reaction? In the photometric method, the material itself is colorful and has very strong absorbance, which can be measured directly. If the material is colorless or with light color, it is necessary to apply appropriate reagent to react with the test material to generate a colorful complex with strong absorbance, followed by the spectrophotometric detection. The reaction in which the measured element is transferred to a colorful compound with the help of a certain reagent is called the Calor reaction, and the reagent is called the chromogenic agent. One single ion can often react with several kinds of chromogenic agent to produce different colored compounds, which possess different analytical features like sensitivity and selectivity. For one specific chromogenic agent, it can react with several kinds of reagents with similar property. Therefore, it is important to pay attention to the following items when selecting the chromogenic agent or Calor reaction for photometric analysis. 1. Good selectivity. The chromogenic agents used should only react with target components to produce Calor compounds, or other components have little interference in Calor reaction. Second, high sensitivity. The produced Calor compound should have a large molar absorption coefficient, usually at 10 to the 4th or 10 to the 5th power magnitude. Third, certain stoichiometric coefficient. The reaction of the chromogenic agent and the target substance should be carried out at a fixed ratio, and the composition of the colored complex should be constant. 4. Stable stability. The generated Calor complexes have good stability, which means that the complexes have acceptable stability constant to avoid being affected by external environmental condition or other chemical reagents in the solution. Only with good reproducibility, the result can be accurate. 5. Obvious Calor difference. The calor difference between calor complex and the chromogenic agent should be large, making the response of blank small in detection. The optimal condition of calor reaction was mentioned before when we talked about drawing the calibration curve. So, what is the optimal calor reaction condition? This is what we are going to investigate next. Factors affecting calor reaction. 1. The amount of chromogenic agent. In order to ensure that the calor reaction is complete, it is necessary to add an excess of chromogenic agents. But not the more the better. The appropriate amount of the calorant should be determined by experiments. In general, the concentration of target components and other conditions are fixed while the different amount of the chromogenic agent is added. Under these conditions, a series of reaction solutions are prepared, and their absorbance is measured. Plotting absorbance A versus chromogenic concentration C, there might be 3 results. Curve A is the most common situation. First, absorbance A increases with the increases of the concentration C, and then it remains constant with the plateauing curve when C exceeds a certain value, which means the amount of chromogenic agent is enough. So the appropriate concentration can be selected based on the plateau part of the curve. The difference between the curve B and A is that when the flat region of the curve appears, the absorbance at some point decreases with the increase of concentration C. So the concentration of chromogenic agent should be selected within the flat region. The curve C is completely different from the above 2 conditions. The absorbance A increases with the increase of C, and no flat region appears. In this condition, it is necessary to strictly control the dosage of the chromogenic agent to obtain the accurate determination result and a complete calor reaction. However, this kind of system is commonly not recommended. 2. Acidity of solution. Many chromogenic reagents are organic weak acids or organic weak bases, which directly affect the acidity of solution, thus affecting the calor of solution. In addition, some metal ions hydrolyze or even precipitate with a decrease of solution acidity, leading to the dissociation of calor complex with low stability. To determine the appropriate solution acidity, fix the concentration of target components, chromogenic agent, and other reagents, and prepare a series of solutions with different acidity, absorbance of which are determined. Plot absorbance curve versus acidity, and the acidity region with highest and constant absorbance is the optimal pH range. 3. Chromogenic time. Some chromogenic reactions are fast while some are slow, and some of the calor complexes easily fade after generation. Therefore, different chromogenic reactions need to be incubated and determined within different time. In practical work, the chromogenic time is obtained from the curve of absorbance A with a function of time t. The time region with maximum and constant absorbance in the curve is the suitable time range. 4. The reaction temperature. It's well known that some reactions require heating, and some chromogenic reagents or calor complexes easily fade at high temperature. In addition, light absorption and calor depths also are affected by the temperature. So the fabrication process of calibration curve and the test of target solution are required to be at the same temperature. In practical work, the reaction temperature is obtained based on the specific conditions from the absorbance curve versus temperature. The temperature region with highest absorbance is a suitable reaction temperature range. 5. The effect of side reactions. For example, the metal ion M and the chromogenic agent R react to produce a color complex MRN. If M has a coordination effect and R has side effect, the completion degree of coordination reaction will be affected. Usually, when 99% of the metal ion has anticipated in coordination, the reaction is considered as complete. 6. The effect of coexisting ions. In photometric analysis, coexisting ions often interfere with measurement. If the coexisting ions themselves have color or can react with a chromogenic reagent to produce a color compound, which have absorption under the experimental conditions, causing high measurement result and the positive error. If the coexisting ions react with a tested component or chromogenic reagent to generate more stable complex of no absorption under the experiment condition, the chromogenic reaction cannot conduct completely, leading to the low determination results and a negative error. Then, how to eliminate the effect of coexisting ions? There are two methods to achieve this aim. First, acidity control. It is a simple and important method to eliminate the interference by controlling the acidity of solution. According to the differences in the stability of the complexes formed by various ions and chromogenic reagent, the acid effect can be used to control the extent of chromogenic reaction, so as to eliminate the interference and improve the selectivity. Second, adding masking agents. Adding masking agents is an effective and commonly used way to eliminate interference. The proper masking agent is required not to react with the tested ions, and its color or the color of the complex formed by reacting with interference ions should not affect the determination of the tested component. Above is information relative to calibration curve for single group determination. First, proper amount of chromogenic reagent and other chemicals are added into a series of standard solutions with different concentrations. Under optimum conditions, the chromogenic reactions are complete, the absorbance of which are measured together with the reference solutions. Plot calibration curve of absorbance in function of concentration. Following the same procedure, the absorbance AX of target sample is measured. The corresponding concentration CX can be obtained from the calibration curve made by the standard solutions. Here are 3 questions for you. First, what are the requirements for the spectrometric determination of chromogenic reaction? From what aspects should we consider about the reaction conditions? Second, how do we make a calibration curve? Third, the silicon content in steel samples is determined by spectrophotometry using molybdenum blue, and the standard curve was drawn with the following data. A steel sample of 0.5000 gram is dissolved and transferred to a 50 milliliter volumetric flask. The absorbance of 0.522 is obtained at the same condition of the calibration curve. Calculate the weight percentage of silicon in the original sample. That's all for today's course, and don't forget to finish the assignments.